All right, good morning, everyone. Question posted earlier. This is a solution to it. And before we proceed further, I would like to us to recall the statement of Kirchhoff's current law because we have to solve for the current in this diagram. We have to solve for the currents first before we get this voltage drop. The question said by using KVL and Ohm's law, calculate the values of V and R1 in the diagram above. So we'll use Kirchhoff's voltage law and Ohm's law to get these values. Before we get that, I want to point out some few things. Originally, the question did not come with this. I had to include that because of I want the diagram to be consistent with the statement of Kirchhoff's current law, because if without an extra current source or sink somewhere within this place, these corners, there will be a violation of Kirchhoff's current law along this branch. So that's why I created these extra sinks and source. However, we are not required to find the value of this current, so that doesn't add to compare. So quickly, before we proceed by doing this, we have to find this current. I'll call this current. Oh, my pen. Okay, I'll call this let's say I1. Then we also have to find this current I2. So how do we get the values of I1 and I2? It's very simple. If you look at this node, you apply KVL to Kirchhoff's current law to this node. You know that the sum of current entering is equal to the sum of current leaving. So that would be equal to 4 milliamps should be equal to 1.5 milliamp plus I1. So that's by Kirchhoff's current law, right? If you apply Kirchhoff's current law to this, you get that. So you get I1 to be equal to 4 minus 1.5, you get 2.5 milliamps. So we've gotten this current. The next is we want to get the value of I2. Remember, this current is actually entering this node. So from here we'll get by KVL again, we would have applying Kirchhoff's current law to this very node here. You'd get current entering is I1. The other current entering is also the 3 milliamps current would be equal to the current leaving I2. Already we've gotten the value of I1, so that means this is I1. That means I2 is equal to I1, which is 2.5 milliamps plus 3 milliamps. So if you do that, you'd get 5.5 milliamps. So that's the value of the current in this branch. So with that, we are ready to apply KVL to get V and R1. So by KVL, by Kirchhoff's voltage law, KVL, you apply KVL around this loop, and then there is this approach you take is, we said, if for instance you are looking for the voltage drop across the resistor, the part at which current enters has a positive polarity, the part at which current leaves has a negative polarity. Same applies for this. So this is a positive polarity, this is a negative polarity. So for this, you can also see that the same applies here. The current 1.5 milliamp enters the positive polarity of the unknown voltage V, and then it leaves through the negative terminal or polarity side. So by KVL, we apply KVL around this loop. Remember, our approach is, if you apply KVL, you take as the if you apply KVL around the loop, you take the polarity of the voltage at which you at your entry point is actually the sign of that voltage, because each voltage has to have its sign, whether it's a plus or a minus. So by statement of KVL, the algebraic sum of voltage drop along closed path equals 0. So I will go, always I do prefer going in the clockwise direction. So we analyze to go around this loop in the clockwise direction. So starting from here, we started from minus V, the unknown voltage, that's the voltage drop here. Then how about the voltage drop here? We know by the statement of Ohm's law, that voltage is equal to the current I1 times this resistance. So it's going to be plus or minus is plus, because we entered through the positive polarity, that is going like this. The first thing is encountered is the positive voltage, so that's why we'll have this plus. So that will be I1 times 1.5 kilo ohms. I will comment on this unit later on. Then the next thing is this voltage drop here along this resistor, so that will be equal to plus as well, because we entered a positive polarity side of the voltage drop across this resistor when we're analyzing. So that will be I2 multiplied by 2, and then no any other element. We are back to the way we started, so equate to 0. So this is a statement of Kirchhoff's voltage law. So that will be minus V plus, what is the value of I1? I1 is 2.5 multiplied by 1.5 plus, what's the value of I2? That's 5.5 multiplied by 2. Everything here equals 0. So if we simplify this, so this is going to be minus V plus 3.75. If you multiply 2.5 times 1.5 plus 5.5 by 2, you get that should be 11. Everything is equal to 0. So make V subject formula. V would be equal to 3.75 plus 11. So from here we get that V is equal to 14.75 volts. So that's one of our solutions. We are asked to find V, and then the next is R1. We know that V, by Ohm's law, V is equal to the current passing through it, which is 1.5. Current passing through this resistor, which is 1.5 times R1. So that means our R1 is equal to V divided by 1.5. If you make R1 subject formula, that will be 14.75 divided by 1.5. So R1 would give, by, if you use your calculator, you have 9.83 ohms as your answer. Sorry, this kilo ohms, right? It's kilo ohm because the current is in milliamps, the voltage is in volts, and most of the time this is common in electronics. This is just like a side talk. If your current is in milliamp, know that your resistance is in kilo ohm, then your voltage is in volts. The kilo ohm, the kilo there will kind of like strike out the milli, because kilo is 10 raised to power 3, milli is 10 raised to power minus 3. So multiplying them will strike the values out, the multiples and sub multiples attached out. So that is it for this question. Thank you for watching.